Cool. Okay, so our speaker today is Misha Fain. Misha is a machine learning researcher at Cookpad, and he's going to present a paper that they've recently published called Backretrieval and Image Pivoted Evaluation Metrics for Cross-Lingual Text Representations Without Parallel-corpora. I hope I said that all okay, Misha.
I have no idea how to pronounce it correctly.
Awesome. Okay, well, we can see your screen now, so I'm going to hand over to you.
Thank you very much, Rich. Yeah, I guess today we're going to have a talk about this magic back retrieval, which is actually a metric. So it is a talk about measurement, and it's talk about particular about measuring text encoders using images. So that you are kind of aware where we're coming from with this. It's a work by Cookpad, and Cookpad's mission is to make everyday cooking fun. So it's all that we were trying to kind of do is kind of related to machine learning in cooking. That's where we're coming from originally. And what we're going to talk about today is because it's about measurements, we want to understand, first of all, what is it we're measuring, these text encoders, multilingual text encoders, why are they needed at Cookpad? And we will discuss how to understand which one of these encoders are best for our purpose, and we'll discuss why these performance measurement is kind of critical for how to innovate and build new models. So the first kind of a setup that I would want to discuss is one of the ways to use machine learning for cooking. This example is about a particular person with a fish sitting in the evening thinking about what to cook, and our platform has a bunch of recipes that have been that are published every day, every hour. There's lots of different people writing up what they've done in different languages, and what you would want is to take a big pile of recipes, put it in the machine learning model, and produce kind of a ranked set of recipes for the users to look at, like a Facebook feed of some sort, that you can have, well, the most relevant recipes should be on the top, the ones that can inspire you to cook. And in this case, you can see that some of the recipes have images, some of the people didn't add images. They could be different languages, like this. Do you see my mouse, by the way? Yeah, so this thing means salmon, so it's kind of related, and it's good if the model puts the salmon recipe at the top, assuming that this person knows Russian, of course. If they don't, that might be a problem. And maybe sushi is also kind of at the top, but the steak and the cake should be at the bottom of the list. We don't really want to show a cake to a person who cares about fish at the moment. So that's kind of the ideal situation that we would that we would want to have. And how we would build such a system? Well, a very standard way to do that, the very first thing you want to do is you would want to take a bunch of recipes and encode them in some way. You would want to encode them in some kind of a multi-dimensional space. So you would create a vector of numbers, maybe 300 numbers, maybe 1,000 numbers for each recipe. And the idea here is that if you have recipes in different languages, you would take the text of those recipes, and your encoder should kind of manage to handle the fact that, you know, that this one is in English, and this one is in Spanish, and this one is in Russian, or whatnot. And you would have some features for images as well, but for users as well, but that's not what we care about right now. Then you would feed all these features to the model, and the model would hopefully figure out how to rank things properly. So the important thing, of course, is what are these features? Like, how do you create them? What is this magic thing that takes text in different languages and produces kind of the consistent set of numbers that correspond to each other? And of course, the features could be good and they could be bad. If you have a bad set of features that are essentially random, then your model is not going to learn a lot. And if your model produces a set of features which is great, then, well, you have a chance of getting something useful out of it, and your model will hopefully give good suggestions to the user. What makes this recipe features good? And I think a good way to look at it is through the kind of reducing the number of dimensions from 1,000 to 2. And in this case, what you can do is you can put them on a map of like XY coordinates. And what you want to have, the situation you would want, is for the recipes that are close to each other semantically, like they are similar to each other in some way or another, and you would want them to be close. Like, for example, these R1 and R2, they're both kind of potato soups, and they should be close to each other. These two other things, these two other recipes, they're both banana bread. One of them is banana bread in English, another one is banana bread in Russian, and you want them to be close. So the idea is that your encoder should somehow abstract out language and should kind of get the meaning of the recipe in the right place. So the location should matter. So far, so good. So the idea is, of course, that if you have such a thing, it's great, because not only you can create this kind of a feature for bilingual users who can see, who can understand different languages, but you can also have other benefits, like you can train a model using more data, because suddenly if you have a consistent features across languages, you can use the data, which is from all the regions in the world. You don't need to constrain yourself to, for example, if you're making a model for people in Hungary, that it's only Hungarian data that you can use. You can use people from America or from Japan. At the same time, you will maintain only one model instead of well, how many languages you have. Like we had CookPad have like, what is it, 35, 40. So it's quite a lot of strain on the infrastructure and on the maintenance of all that stuff. So if you have one, it's much easier. So there's a lot of benefits of having these encoders. And in fact, it so happens that a lot of other companies and researchers are already exploring this idea for quite a while, and they are building these something called cross-lingual encoders. They do exactly what we just described. They take a piece of text, they put it in some big neural network, and it spits out a bunch of numbers, which is a vector. And what they claim is that if you put these numbers in a two-dimensional space, that if you put different puppies, they're going to be closer to each other in different languages. I can't read Chinese, but I assume it means cute puppy. And the nice weather would put the nice weather text will be next to a nice weather text in all different languages. So it's exactly what we want. So problem solved. Yeah. Of course, there is never a problem that's solved by somebody else for you. You're kind of stuck because, well, first of all, there is a big difference between puppies and recipes. You don't know whether it works or not and how well it works for recipes. Second, every company, not even a company, every department in the company seems to have built their own model, which is completely different from all the other models. There is one that's called Lapse from Google. There is one that's called Laser from Facebook. There is another one called UseM from Google. And there is another one from Google. And you can also use Google Translate, and you can use a Facebook translation. You can also use various universities, like all these MIT, Stanford's groups who create similar models as well. They're all open source. You can download them, you can use them. Which one of them should you do? And maybe all of them are bad. Maybe what you need is to build your own. And maybe you can name it in some fancy way. For us, it would be like CookBird or something trendy for those people who follow this literature. We don't know. And the problem is that building them is also a lot of work. So you don't really want to kind of just blindly do it. You want to know what you're doing, because you need to feed the massive data sets to these models for them to work well enough. And deploying each model in production is also quite hard. Like these models are heavy. They are like worse than image models in the sense that they are really, really big. They have like billions of parameters. Some of them, actually, I don't know, maybe not billions for these ones, but they're close. They get it there for sure. And can we do something, simpler offline first before we do all this work of training and deploying this? Can we test them offline? And there is a very simple way to test them, of course. If you have a set of text in different languages, like you would have a Spanish and English, you could set up a retrieval task. And what you would do is you would take a random recipe from Spanish, you would get their vector, and you would get a random set of candidates from English recipes, and one of them would be a matching one. So in this case, salmon is matching with sushi. And what you would want is you would want to do this kind of a multidimensional magic and find the closest recipe to your query among the candidates and rank these candidates by closest, basically. And if the closest recipe ends up on top, it means that your encoder is great because the closest recipe is the one that's actually the matching one. So that would have been great. So in this case, your model, if it manages to put the matched one at the top, it gets a score of 1. Maybe some other encoder is not so good, and the space is not that good. So in this case, maybe this matched sushi recipe ends up at the bottom of your ranking, and in this case, you get 0 points for this particular score. So different encoders will have different scores, and the idea is to see which one. So if you have 2 different encoders, the idea is to plug them into this task, and you see which one of them achieves a higher score. And of course, you select many different queries, and you have many different sets of candidates, and you average the result. And what you come out with is a kind of a table which gives you scores for each encoder per data set. So you have a data set from that, for example, this particular data set, which is about some people which are doing some random things, and there are descriptions of what they're doing in English and in Japanese. And if you do this kind of a procedure of retrieval, if you put one model, the score might be like 73% of the time it returns correct results, and the other one might say 58% of the time it returns correct. So you can say that maybe this one is better for this data set, for this pair of languages. Maybe if you translate it backwards or try to retrieve it backwards, it's not as good, for example. And maybe if you have another data set, for example, if you have desks and chairs and you try to retrieve chairs and desks, then maybe these models will perform differently. In this case, maybe some other model will do best. And some model might be bad on all the data sets, and some model might be good on all the data sets. So it's how you can evaluate your models, which would be perfectly good. The only problem is that this evaluation method requires you to have parallel data. And it requires you to know what is the correct result. So if you remember here, we know somewhere in the data set would say that, oh, this salmon is matching with this sushi. And unfortunately, that's just not always available. And usually it's not available. At Cookpad, it's definitely not available. We have a bunch of recipes created by different people in different countries. They don't copy them. They created them from scratch. So we don't know which one is matching to which one. We have no clue. In general, it's a problem. Like, okay, if you have a soup and you have a banana muffin, it's pretty easy to say that these two recipes are not similar to each other at all. And if you have 2 banana muffins made by different people, you would say that they're similar to each other. But if you have something like fruit salad, which has bananas, or strawberry muffin, which doesn't have bananas, but it's a muffin, then you start thinking, well, which one is more similar? Well, it's a question, and it's not easy to say which one is more similar, which one is not. It depends on, I care about ingredients, or how do you cook, or maybe I use in the oven or not, which language it is, which cuisine it is, or all of it together maybe. It really depends on, there is no good answer. You don't know. Well, you don't know, that doesn't necessarily mean that you should do nothing about it. Maybe you could still find some experts, and you can ask them, okay, maybe you're bilingual, you know Arabic and English, and maybe you can get queries from Arabic and candidates in English, and you can rank the results, and you can create your test set like that. That would be perfect if you're translated from English to French. But if you're translated from each language to each other language, you're in trouble, really. Because it's kind of quadratically grows. If you have 5 languages, you got 25 test sets to make. And basically, yeah, it gets worse and worse. If you have 30 languages, you need 900 test sets to make. And you also need people, obviously, who speak these combination of languages, which is gets harder and harder progressively. Like some of our popular markets are in Indonesia and Hungary. And we have a lot of people who speak Hungarian, a lot of people who speak Indonesian in the office, but as far as I'm aware, none of them speak both of them at the same time, and they are relatively popular languages. So what we decided to do is we decided to approximate this retrieval with some kind of an approximation, which we call backretrieval. And the idea of this backretrieval is that you would have a set of text in a source language, for example, Spanish recipes and English recipes, but you would not know which ones of recipes are matched with which. So it's exactly the setup we have. And you have some text encoder that you want to evaluate. the way it would work, I'm just going to walk you through the process. It's a bit convoluted. So what happens is you would set this set of recipes in Spanish, set of recipes in English. They're not really matching. You see, like there is a cake here in Spanish and there is a cake here in English. So maybe they're both kind of matching, but the rest are really not. So what you would do is you would select a random query like before. Like you can, I guess the first thing actually you do is you get rid of all the images to start with, because what you want to do is you want to test the text encoder. So you forget about images for now. You select a random query. In this case, it would be a tuna Spanish recipe. And then you rank the English recipes by similarity to the tuna recipe using your encoder. You don't know which one is correct, but your encoder picked this one, salmon, as the closest because the similarity is the highest. So it thinks that the salmon is the best match for tuna. So far, so good. It can be right, it can be wrong. In this case, I would say, well, it's all right. Salmon is kind of close to tuna-ish. Maybe it could have been, I mean, I don't know. Maybe sushi is a better match. Not sure. But it's definitely more better match than a steak, for example. Then what happens is that we bring back the images, and so we select this image that is matching the one that the model thought is the correct answer. Then what we do is that's kind of this back retrieval step. We get rid of texts completely, and that's what we're stuck with now. We have this image that we think is the right match. And this was the red image, is the one that we started with. So that was the query image to start with. We didn't use the image, we used the text, but that's the image corresponded to that text. And now what we do is we try to rank by similarity, by image similarity, all the Spanish recipes, Spanish images, by similarity to this selected proposed English image. And in this case, if we do that, we could see that, well, in this case, this particular image is actually the closest visually to the one that the algorithm selected using text. And in this case, we say that we successfully completed this task with this particular encoder. So to walk you through this again, because maybe especially break it, we first get rid of images. We use the text encoder to select a proposed match, and we use the image that's corresponded to this proposed match to search through the original set of images from the original language from Spanish, and we see whether we manage to rank the image that corresponded to the text that we started with at the top of our search of our kind of image retrieval results. That's what we do, and just as an aside, how would you do this image ranking? There are, again, many ways to do that. And one of the good things about this algorithm, it seems to be quite robust against what exact method of image searching you're using. One way to do that is by embedding every image using some convolutional neural network that's pre-trained on a big data set like ImageNet. And we just use that representation to kind of to search for the closest one among the candidates. That's really not really important here. The point here is that there is some fixed method of searching by image that exists. And maybe for another encoder, that's I would say not such a good one. Maybe if you do exactly the same process, it will select, well, a bad match. Like that one selected a salmon, which was okay-ish, but this new encoder selected a cake as the best match. That's a bad one. So if you do exactly the same thing, what it would do is would select this cake image as a proposed image. And when it would try to rank the original set of images from Spanish, what it would do is that it would find, of course, the cake as the closest image. And the idea is that, well, this tuna image will not be close to the top of the search results, and you would get a 0 score for this one. So it's just a different way to measure the score. And in this case, you would get exactly the same situation as before. You would average the results across different queries and different candidate sets. And the only difference with the previous slide is that there is a back retrieval score rather than a regular retrieval score. And what you would have here is another table. Well, the numbers here are the same, but you could see that they could be different. And you could also select, okay, this model is better than that model on this particular data set. Of course, in this case, the advantage is that you don't need your ground truth. You don't know what, you don't need to know what is the matching result. You just need a bunch of images. Well, the problem is, of course, how do we know it works? Like, I just gave you this nice intuition of why it would work. Maybe not that nice, but at least some kind of intuition. And the question is, like, why do you think that it actually works in practice? Maybe it's just garbage. Maybe just the numbers that it spits out don't make any sense. How do we know that it's any good? Well, if we knew what the correct answer would be, then we could compute the regular kind of original type of retrieval score. And then we could compare it with back retrieval score. And the idea is that what you would want is that if you have a model which scores high on this back retrieval measure, this model should also score high on the original kind of this retrieval score if you would have known the correct answer. And if you score low, of course, you should get a low score. So that's the idea. And you would need a data set where you know the correspondences to test this, the fact that this correspondence actually exists. There are 3 public data sets we found that actually match these requirements. All these data sets, they have different sets of images in different languages, and they have information about which text is matching to which text. So you know that, for example, this particular text is matching to that particular text. So it's exactly kind of what we would want. If you would try to run this method on different encoders, this is kind of what you would want to achieve. You would want a situation like that, where you would take an encoder, you would compute an actual kind of this ground truth retrieval score, and then you would compute a back retrieval score. And you would want a situation where if something scores higher on a ground truth retrieval score, it should also score higher in the back retrieval score. So if you say that if you don't have a ground truth retrieval score, you just have this approximation one, you say, oh, this one did better, it scored 1.0.1 here and it's 0.04 here, I would expect it to be better. Then this model should be better than that one. And what you don't want is this. What you don't want is the situation where the back retrieval is kind of just random. Like, yeah, it scored highly for one model, but it doesn't mean anything, because if you do the real test, then it will be garbage. Like, this particular model performs really bad on the actual result score, but really good on back retrieval. So it's kind of a hypothetical scenario that you don't want, and this is a hypothetical scenario that you want. Now the question is, what actually is true in the world? If you actually do this experiment, what is going to be the result? And how is this graph going to look like? And it actually looks like this. It's much better than random, for sure. It's not a perfect line, yeah, but still, mostly, you know, if it's actually pretty much everywhere. If the model scores higher on back retrieval, it also scores higher on ground truth. It's almost not quite a straight line, of course, but it's getting there. And that's actually really, really good, because it means that our model is, our metric is reliable, and we can use it in the absence of the original one. And we tested it in a bunch of data sets. We tested it across different sets of languages. Like, the type of data we use is very different. This one is data, like these ones are like tables and chairs, and this one is like people riding bicycles. So it's a completely different types of data, and on each of them we have a very high correlation between these 2 sets of metric. The idea is, of course, that that in the real world, where you don't have that, you should be able to trust this metric enough, and it seems like you can, or to some extent at least. We put all the details in the paper, which is going to be published at one of the leading information retrieval conferences, with the great help of Neil and Danushka, one of our collaborators from University of Liverpool. Yeah, so if you want to learn more about the details, you can have a look. It's quite short. It's like 4 pages, so should be able to go through it relatively quickly. Back to recipes, what do we do with this? Now, you remember, in recipes, we don't really have the correct answer. So we can take this back retrieval measure, and we can take all the different sets of languages, and we can compute the numbers for each combination of languages. And suddenly, we have a lot of data. We can you know, we could do a lot. So we can see how good is particular encoder for retrieving from English to Indonesian. Like, well, some number, 4.9, and some other encoder has only 2.6. It's much worse. It's like twice worse. But for some other language, it could be almost the same. So it really kind of, some models perform, we found that some models consistently perform good for some languages and not for others, for example, and things like that. Like, it's really, you have a wealth of information about how to compare models, and it's kind of all automatic. You don't need any labeled data for this, which is really exciting. And what we did is we compared a bunch of different, I guess, different methods that are available kind of open source, and we trained our own model. And what we found is our own model, kind of on average across all the language pairs, performs way better than, well, not surprisingly, because the other people don't know about our data set. So it's not that anything particular to be proud of. I guess what to be proud of is that we managed to measure this. That's the important bit. And moreover, we can actually have a look at the details. So we know that, for example, even if on average the performance is better, for some language pairs, like for example, translation to Arabic on this particular model is really bad, even compared to the baseline. But if we do some tweaks to our model, then the performance improves. So we can actually do quite detailed a look into how these models perform, and we can select the one that works well across the board. And we took this model and we did some kind of a downstream task testing, because all of this is like retrieval. But what about some more realistic tasks? And we tested it on some kind of a manually labeled small data set for one particular language pair. As you can see, English to Russian. We saw that the results are consistent, and we tested it on cook and feed interactions, which is on our website, and we tested it on search ranking, again on the CookPad platform, and all of the results were consistent with the scores we got for Backretrieval, which is a really good sign. It just says that our metric is reliable, so we can actually trust these table. We can trust what it says about how well it works across the board. And we haven't deployed it live. That's kind of work in progress at the moment. So we're excited to see it hopefully working soon in our platform. Yeah, in short, we discussed that text representations are kind of a key piece of many real-world systems, including most of what CookPad is doing, because we deal a lot with recipes. And there are exciting infrastructure and UX opportunities in this idea of projecting the text from different languages into the same space, as many companies are recognizing now, because it saves you a lot of infrastructure headache, and also allows you to do more exciting models and features for your website. But the problem is to choose the right method. And because some of them work really well for our problem, and some of them are working really badly, even though both of them look fancy and have cool papers and a lot of people using them. So the fact that it doesn't mean that it would work for your application, the fact that it's used by many people somewhere else. And you should be able to test that. And the idea as represented here is that if you have no parallel data available, you can still do something. It's maybe not as perfect, but it's a decent approximation. You can use this Backretrieval to evaluate the models, and this way you can drive the improvement. That's pretty much it. Thank you very much. Well, we're hiring, I guess. Should always say that. We do. Please.
Yeah, you can say that. That's fine.
Please look at our website. We have a lot of different roles available now. Yeah, and if you have any questions, I'm happy to answer them.
Cool. Thanks, Misha. I've got a couple of questions. If anyone else has got questions, because we've got quite a manageable amount of people on the call, I could probably actually unmute you. So if anyone wants to just chat and sort of create a discussion, let me know, and I'll just raise your hand, I think, and I can unmute. But I can start by asking some questions. So you talked about the comparing image similarity using the it was a CNN of some kind, and you were sort of comparing those encodings in the final layer. Did you find that you could just use an off-the-shelf image classifier for that, or did you have to train something more specialized that, based on food and recipes and things?
I guess the answer is you can use a off-the-shelf one. And that's, to some extent, is a bit surprising. But what we found is that basically, even if this model is better than random, even a little bit, it already is helpful. What's happening, if you use a model which is really good at detecting similarity in images, then this scale increases. Like you see these numbers here, they are like 0.0 something, and here they are 0.1. So the scale is different. So if you have a model which is worse, then basically the scale just becomes smaller. But the relationships remains relatively constant. So surprisingly, we found that actually you can use off-the-shelf model. You don't need to retrain it. If you retrain it, it doesn't hurt. You might have more power, like more statistical power. But besides this, you can use off-the-shelf models.
Because I was going to sort of lead to my second point, which was about that, I guess, sort of you can understand like comparing if two chairs are similar or something, but when you look at a recipe, the recipe might have the same sort of key ingredient on the top of the plate, but it's actually a very different recipe. It happens to use a similar ingredient, perhaps. So I was just wondering whether that sort of, what is it that is similar about two recipes?
Yeah, so I think the reason why it works, even with very kind of noisy image similarity, as you pointed out, like it's, especially by looking at the image, it's not always easy to say, like how do you distinguish two soups from, like by vision. But the idea here is that the reason it works to some extent is because of these mistakes are uncorrelated with the mistakes that the text encoder is doing. So it's like a noise. It's like a set of noisy labels. It's the same thing. If you have a set of very noisy labels for your data, and then you try to measure the performance of your model, you would have some value. And if your noise is relatively evenly spread, then you could still compare two models, even if your labels are very noisy. It's just the noise will average itself out. And that's the same idea here. It seems like these kind of problems that you described, they tend to average themselves out across a big enough test set.
Yeah, that makes sense. And then I guess my other question was around so obviously you've used some publicly available data sets, but you sort of alluded to the fact that you were using sort of internal data sets. Do you know like roughly how large those data sets are? I mean, are you training it on everything that Cookpad has, or is it a subset? So
you mean the training the model or evaluating?
So the evaluation, sorry, yeah. Yeah,
so for evaluation, the problem is about statistical significance here. Like if you have about, I'm going to tell you, like, because there are no confidence intervals here, but the confidence intervals here is going to be like very small, like this big maybe. And the size of the data set here is maybe it's 10,000. So if you have 5,000, the confidence interval is still quite small. If you have 1,000, you can still, if you have 1,000, size of the test set is 1,000, it becomes a bit more, it starts overlapping slightly. So if you have 100, it's too small. You need like at least 1,000, 1,000 candidates, basically. Your test set should be at least 1,000, I would say. Yeah, if you have 3,000, it's better. If you have 5,000, it's even better. If you have 10,000, you don't need any more at all. So that's cool. If you have 10, it's too little, of course. Like if you have 3, then it's garbage.
Sure. And is this something that will be open source, or is this something that is IP to Cookpad?
Well, we can actually maybe we should obviously consider. We will consider it open source in it. We haven't done that yet, but the code is very, very simple, to be honest. It's like one Python script. Basically, the only thing we need to do is we need to clean it up so that it can be used standalone without anything extra. And I think that's the main. Our laziness is the main obstacle to this, rather than anything else.
That'd be cool. I think a lot of people would be interested in just sort of seeing hands-on how it's implemented. Cool. Okay. Well, last chance for anyone else on the call to ask a question. Otherwise, I think we'll wrap up. Okay, well, awesome, guys. Well, thanks very much, Misha, and yeah, we look forward to reading the paper.
Thank you very much. Thanks a lot for listening.
Cool. Thanks, guys.
Have a good day.